All right, so I'm going to finish going over the examples that we didn't get to go over in class today. So we want to find the numbers at which f is discontinuous, and we want to know at which of these numbers is f continuous from the right, the left, or neither. So we're going to look at this graphically first. So we have a piecewise function here. I'll graph the line f of x is equal to x plus 2 when x is less than 0. So that's going to be a line with a y-intercept of 2, a slope of positive 1. So the line is going to look something like this. And again, it's just less than 0, so I don't want to include that point. And then I want to graph the 2x squared when x is between 0 and 1, including. So when I plug in a 0 over here, that's going to give me a 0, 0. When I plug in a 1 over here, that's going to give me the point 1, 2. So the second part of my graph is going to look probably something like this. It's quadratic in nature, so it's going to be curved a little bit. And then 2 minus x when x is greater than 1. So that's going to be a y-intercept of 2, a slope of negative 1. And I'm going from x greater than 1. So here probably looks something like this. All right, so we can definitely see that we have some jump discontinuities going on here. And we're going to be talking about continuity from the left, right, or neither. So we know that we are discontinuous at the x value of 0 and the x value of 1. So x equal to 0 and x equal to 1 are our discontinuities. So if we're looking from the right and from the left, we want to know, are we continuous from the right or from the left at x is equal to 0? So if we look at this graphically, we can say, all right, well, from the left, that's not where our function is defined. But if we're coming from the right, then that's where our function is defined at 0. So at x is equal to 0, we are continuous from the right. Just by looking at this graphically again. We'll kind of get more into that in a second. So then if we look at x is equal to 1, we can actually see that this is going to be continuous from the left, because if we're coming in from the left, this is where our point is defined. If we're coming in from the right, our point is not defined here. So we are continuous from the left. Okay, so that's just by looking at the graph. Well, what if we wanted to do this algebraically? Well, if we look at the piecewise function, we know that when x is less than 0, we're coming in from the left. So this is saying that that is from the left. When x is greater than or equal to 0, that's when we were coming in from the right. So over here is where we're coming in from the right. And you can actually see in your inequality that your x value is equal to 0 here. So our continuous from the right, you can actually see that in the inequality. So if x, the 2x squared, if we're saying x is less than or equal to 1, this is where we're coming in from the left. And again, since the x is less than or equal to 1, you can see that right here in our inequality, that's where we're going to be including the point. So again, from the left, that's where we said our point was defined. So that's why we were continuous from the left here. And over here, if x is greater than 1, again, that's where we're coming in from the right. So we can see that our point is not included from the right. So just by looking at the inequalities, you can see that. And then by the graphs, you should be able to see the continuity from the right and from the left. All right. So example 3 is just kind of putting things together and sketching your own graph. So there's a ton of different ways that you can do this one. I'll just kind of give you an example of how I saw it. So we want to sketch the graph of a function f that is continuous except for the stated discontinuity. So we have discontinuities at -1 and 4. These are talking about x values. But we're continuous from the left at -1 and we're continuous from the right at 4. So basically what that tells us is that over here, the limit as x is approaching -1 from the left of f of x must be equal to f of -1. That's what it means to be continuous from the left. Over here, what we're saying is that the limit as x is approaching 4 from the right of f of x must be equal to f of 4. So that's where the point must be defined. Here's where this point must be defined. Whatever is going on around this, it really doesn't matter as long as you're fulfilling these kind of stipulations. So I know that we need to be continuous from the left at -1. So it doesn't even really matter where you put your point. I'm just going to choose to put it here. And I know that this point has to be defined. And I can basically do whatever I want with this side of the graph, as long as we're continuous from the left. And that point is defined as my graph is coming from the left. And then I know that we have to be continuous from the right at x equals 4. So 2, 3, 4. You can put a point anywhere. It really does not matter where you put it. And again, you can do whatever you want with this piece of the graph over here. I'll just kind of make it easy and say, okay, what if I have a horizontal line that way? This is where we're continuous from the right, because I'm approaching from the right, and here's where my point is defined. And basically anything can happen in between here. Like I can just put like, I don't know, some sort of linear function here. So as long as you're fulfilling these two stipulations, it really doesn't matter what your graph is going to look like. I just usually like to keep it simple, but you can do whatever you want. All right, and example 4. So for what value of the constant c is the function f continuous on all real numbers? So we know that continuous means that we need to make sure that our limit as x is approaching some value must exist. So if we look over here, we can see that there's probably going to be a problem with 3. So I'm going to say I'm going to want to know that the limit as x is approaching 3 from the left of f of x must be equal to the limit as x is approaching 3 from the right of f of x. That's what it means to have a limit exist. And my function must be defined at x equals 3. Okay, so what does that mean? Well, I'm going to first calculate the limits. So let's do the limit as x is approaching 3 from the left. And from the left, again, we were kind of talking about this in class today. From the left means that x is less than 3. So I'm going to go ahead and evaluate the x cubed plus cx at 3. And again, I can just use direct substitution here for all my x values. So 3 cubed plus c times 3. If I simplify this, this is really going to give me 3c plus 27, which really doesn't help much, but we'll see kind of our next steps in a second. I'm going to calculate the right-hand limit next. So the limit as x is approaching 3 from the right. And from the right, we're talking about this bottom function. So the cx squared minus 4x. And again, I'm just using direct substitution here for my x values. So c times 3 squared minus 4 times 3. That's going to tell me this is 9c minus 12. And we know that these limits must be equal, right, in order for the limit to exist. So I realize that we have variables here, but so the limit from the left and right must be equal. So to solve for c, if I were to set these two equal to each other, I should be able to solve from here. So 3c plus 27 is going to be equal to 9c minus 12. It's going to be 27 is equal to 6c minus 12. That'll give me 39 is equal to 6c, which will give me 39 over 6, which I can simplify to 13 over 2. So the value of c that makes this function continuous, meaning the function is defined at 3. So if I were to look at this graphically, that would mean that there's no holes at the x value of 3. And I'm proving that the limits from the left and the right must be the same. So the c value here that makes this function continuous would be 13 over 2. So it's your turn to try the homework problems. I will post the even answer key at some point this weekend. Please let me know if you have any questions on anything.